In 1960, two men descended nearly 7 miles beneath the Pacific Ocean and reached the deepest point on Earth. It took more than 50 years for anyone to return. Since then, only a handful of people have visited Challenger Deep. We often assume that once humanity achieves something, it remains within reach. That progress moves forward. But the bottom of the Mariana Trench is not a place we can access whenever we choose. Every descent requires a highly specialized submersible, engineered to survive pressures more than 1,000 times greater than at the surface. Only a few such vehicles exist. Fewer still are operational at any given time. There is no permanent station below, no infrastructure, no rescue system. Each mission is temporary. Each relies on funding, political will, aging technology, and materials that operate at the limits of physics. And that raises a quiet but uncomfortable possibility. Reaching the deepest place on Earth is not a solved problem. It is a capability that must be rebuilt, maintained, and justified over and over again. If those conditions disappear, so does our access. So, what does it really mean to say we have reached the bottom? Is it a frontier we now own, or a place we visit only when resources allow? And could there come a time when no one can go back at all? Tonight, we examine why the deepest point on Earth may be slipping once again beyond our routine reach. But before we begin, if you enjoy these journeys, gentle, soothing, and quietly filled with wonder, I would be grateful if you gave this one a like and perhaps tapped subscribe. It helps other curious dreamers find their way to this peaceful little corner of the internet. And if you would be so kind, let me know in the comments, where are you listening from tonight, and what time is it where you are? It is always a joy to see how far across the world this little sleepy corner of science travels. Now take a slow, deep breath, let your shoulders loosen, and let's begin the descent. Far out in the western Pacific, where the ocean stretches without interruption for thousands of miles, the seafloor begins to bend. It does not break at first. It curves almost gently, as if yielding to a weight too immense to resist. Beneath that quiet arc lies the Mariana Trench, a vast scar in the planet's outer shell, extending for more than 1,500 miles along the boundary of colliding plates. From above, nothing in the surface waters reveals it. Waves pass over in ordinary rhythm, unaware of the descent unfolding far below. The trench exists because the Pacific Plate is slowly sliding beneath the smaller Mariana Plate, a process known as subduction. This movement is not sudden. It advances by mere centimeters each year, patient and relentless. Over spans of geological time, that steady convergence forces one slab of lithosphere downward into the mantle, pulling the seafloor with it. The result is a narrow, elongated depression that deepens as the descending plate bends and sinks. Gravity assists the motion, drawing the heavier crust into warmer layers beneath. At its southern end lies Challenger Deep, the lowest known point in any ocean. There, the crust has been dragged farther down than anywhere else on Earth's surface, forming a basin within the trench that reaches nearly 7 miles below sea level. Yet even this depth is not fixed. The plates continue to grind and shift, redistributing sediment, adjusting slopes, and subtly reshaping the contours of the abyss. What appears on a bathymetric map as a clean outline is in reality a landscape in motion. Ocean trenches are among the most unstable environments on the planet because they sit directly atop active subduction zones. Stress accumulates where plates lock together, then releases in earthquakes that ripple through rock and water alike. These tremors can trigger underwater landslides, sending cascades of sediment downslope into the deepest pockets. Fine particles drift downward from the waters above, settling into layers that may later be disturbed again by seismic pulses. Even the angle of the descending plate influences how the trench evolves, altering its width and the steepness of its inner walls. Heat from the mantle rises along fractures, interacting with seawater that seeps into cracks and returns enriched with minerals. Chemical gradients shift as fluids circulate through buried crust. The trench is not a static canyon carved once and left untouched. It is an active boundary, a place where the surface of the planet is continuously recycled. Rock that once lay beneath open sky is carried downward, transformed by pressure and temperature, and eventually melted or folded into new forms. In this slow collision of plates, the Earth reveals its restlessness. The Mariana Trench is not merely a depth measurement on a chart. It is a dynamic edge of a living planet, shaped by forces that operate far beyond the span of a single human lifetime, yet close enough to feel the tremor of shifting ground. Long before metal begins to bend, the ocean itself becomes the dominant force. With every 10 meters of descent, pressure increases by roughly one additional atmosphere, layering weight upon weight in a steady mathematical climb. The change is invisible, without sound or color, yet it accumulates with absolute consistency. By the time a vessel has traveled a few hundred meters, the surrounding water is already pressing with a strength far beyond what human senses can detect directly. At greater depths, that quiet arithmetic becomes overwhelming. Water resists compression. Unlike air, which can be squeezed into smaller volumes, seawater yields only slightly under immense force. Its molecules sit close together, transmitting pressure efficiently in all directions. This is why the ocean does not merely press downward, it presses inward from every angle at once. The hull of a submersible does not bear weight on its roof alone. It carries it across every square inch of its surface, evenly distributed, relentless, and constant. Force applied from all sides creates a specific kind of danger. In open air, structural failure often means explosion, an outward burst as internal pressure exceeds what a container can hold. In the deep sea, the dynamic reverses. The pressure outside vastly exceeds the pressure within. If integrity fails, the ocean does not seep in gradually, it collapses inward. An implosion unfolds in milliseconds as the surrounding water rushes to occupy the space that resistance once held back. The energy released is brief yet catastrophic, generated by the sudden compression of trapped air and the instantaneous displacement of structure. Depth multiplies this risk exponentially because each increment adds not just more force, but more stored potential energy in the surrounding water column. A small descent deeper does not represent a small change in consequence. It represents a compounding of stress. Materials that perform reliably at moderate depths encounter entirely different demands when subjected to thousands of meters of accumulated pressure. Microscopic imperfections, invisible during inspection, become critical under such conditions. Even the smallest crack can transform into a point of failure. A flaw measured in fractions of a millimeter concentrates stress along its edges, weakening the uniform distribution that spherical designs depend upon. Under extreme pressure, that concentration can propagate rapidly, spreading through metal or composite in a chain reaction. What appears solid and secure at the surface behaves differently when surrounded by a medium that refuses to compress and that presses with unyielding symmetry. The hostility of the trench is not born from turbulence or chaos alone. It arises from physical laws applied with unwavering consistency. Gravity pulls the water downward, and the water transmits that pull in all directions. The deeper one travels, the more completely those laws assert themselves. In that environment, survival depends not on strength alone, but on precision, on flawless geometry, on materials that endure forces beyond ordinary experience. Failure at extreme depth does not unfold as a gradual surrender. It arrives as a sudden rearrangement of matter. The surrounding ocean, already pressing with immense uniform force, requires only the smallest compromise to begin its inward surge. When structural integrity falters, collapse occurs in milliseconds, faster than conscious perception can register. There is no extended warning, no slow flooding. One moment there is separation between inside and out, and the next that boundary is erased. Inside a pressure sphere, the air remains at near surface conditions, carefully regulated to sustain life and instrumentation. Outside, the water carries the weight of miles above. The difference between those two states contains stored energy, held in tension by metal, composite, or alloy. If a fracture propagates beyond control, the external pressure compresses the internal air almost instantaneously. Gas that once filled a chamber at normal density is crushed to a fraction of its volume in an instant, releasing heat and shock as it yields to forces it cannot resist. The energy release is violent yet brief. It does not resemble the outward bloom of an explosion seen in open air. Instead, it is an inward collapse, a rapid convergence of structure toward a single point. Components shatter, fragments accelerate, and the surrounding water rushes to occupy the space that seconds earlier contained air and equipment. The entire sequence completes before any meaningful response could occur. Instruments record a spike, then silence. At such depths, rescue is not a viable concept. The distance alone prevents immediate intervention. Even if a support vessel on the surface detected an anomaly at once, the time required to descend would far exceed the duration of the event itself. There are no nearby platforms, no fleets stationed in readiness. The environment allows no margin for delay. Recovery, when possible, is an act of later investigation rather than timely assistance. History offers quiet reminders of this reality. Over the decades, submersibles operating in deep waters have experienced structural failures, some during testing, others in operational contexts. Each incident has reinforced the uncompromising nature of pressure at depth. Designs have evolved in response, incorporating thicker hulls, refined geometries, and rigorous inspection protocols. Engineers study fracture mechanics, metal fatigue, and the behavior of composite materials under cyclical stress, seeking to predict and prevent the smallest weakness. Safety margins in deep ocean engineering must therefore be extreme. Components are rated well beyond anticipated loads, and every weld, viewport, and seal is scrutinized for imperfection. Redundancy is built into life support and control systems, yet no redundancy can counteract a catastrophic hull breach once it begins. In this realm, prevention is the only defense. The physics that govern implosion allow no second chance, only the quiet insistence that boundaries be respected without compromise. Before any descent begins, long before a support ship turns toward open water, the most important journey has already taken place inside a workshop. There, engineers shape metal into geometry that must withstand forces beyond ordinary intuition. At the heart of every full-depth submersible rests a pressure sphere, a form chosen not for elegance, but for necessity. A sphere distributes external force evenly across its surface, allowing stress to flow without concentrating along edges or corners. In this symmetry lies survival. When water presses from every direction, flat panels flex and seams become vulnerable. Angles invite imbalance. The sphere, by contrast, offers no preferred direction for failure. Each point on its surface supports the next, creating a continuous path for stress to travel. The material itself becomes a shell of shared burden, each molecule contributing to the integrity of the whole. Precision in machining is essential because even subtle deviations in thickness can alter how pressure is carried across the structure. Materials chosen for these spheres must balance strength, weight, and resilience. High-grade steel has long been valued for its predictable behavior under compression, yet it adds significant mass. Titanium offers an appealing combination of strength and lower density, resisting corrosion while maintaining structural integrity. More recently, advanced composites have entered the conversation, promising reduced weight and tailored performance. Yet composites behave differently under repeated loading, and their internal structures can conceal microscopic damage that is difficult to detect from the outside. Each dive subjects a vessel to a complete cycle of stress, from near surface conditions to immense compression and back again. Over time, these cycles introduce fatigue. Metal lattices experience subtle shifts, tiny imperfections propagate, and cumulative strain alters properties once considered stable. Engineers model these effects through finite element analysis and laboratory testing, yet real-world exposure at extreme depth cannot be replicated perfectly on land. The ocean becomes both proving ground and examiner. Certification of a full-depth vehicle is therefore complex and deliberate. Independent review boards analyze design calculations, material specifications, weld quality, and inspection protocols. Non-destructive testing methods, such as ultrasonic scanning and radiography, search for hidden flaws within thick hull sections. Every viewport, seal, and penetration point must meet rigorous standards. Even then, certification represents confidence within defined limits, not absolute certainty. Because of these demands, only a very small number of submersibles are capable of reaching the deepest parts of the ocean. Building one requires substantial investment, specialized facilities, and teams experienced in extreme engineering. Maintaining operational readiness demands continual inspection, refurbishment, and recalibration. A single vessel embodies years of design, testing, and refinement. In that fragility lies a quiet truth. Access to the deepest ocean depends not only on courage or curiosity, but on machines whose perfection must be renewed again and again, dive after dive, without compromise. In the early years of deep ocean exploration, long before modern composites and digital telemetry, a bathyscaphe named Trieste prepared to descend into water few believed could be reached. It was a craft of another era, suspended beneath a massive float filled with gasoline for buoyancy. Its pressure sphere forged from thick steel. The design was ingenious in its simplicity, relying on basic physical principles rather than advanced electronics. On a winter day in 1960, it began its slow journey downward into the western Pacific. Inside the sphere, two men monitored gauges and listened to the subtle sounds of their vessel adjusting to the increasing load. The descent unfolded over hours, a steady sinking through layer after layer of ocean. At several thousand meters, a loud report echoed through the cabin. One of the outer acrylic viewports had developed a crack in its outer layer, a sudden reminder of the strain pressing in from all sides. The inner barrier remained intact, and calculations suggested that the sphere itself retained its strength. After assessment, the descent continued, guided by measured restraint rather than haste. When Trieste finally reached the seafloor at Challenger Deep, it settled gently into fine sediment. The occupants observed a pale landscape illuminated by external lights, a quiet plain at the lowest known point on Earth. They remained there for roughly 20 minutes, long enough to confirm their position, take limited observations, and record essential data. Communication with the surface was minimal and slow, carried through acoustic signals that traveled patiently upward. There was no elaborate exploration, no extended survey. The mission's primary achievement was arrival. The ascent required releasing ballast and waiting as buoyancy overcame gravity. When the vessel surfaced, it carried proof that human engineering could survive the greatest depths. Yet the feat did not usher in an era of frequent returns. Instead, years passed, then decades, without another crewed visit to the bottom. The technology required for such descents was specialized and expensive, supported by limited funding and narrow institutional interest. Space exploration captured public imagination and national budgets, while the deep ocean remained largely out of sight. Engineering challenges also contributed to the pause. Materials science in the following decades advanced steadily, but full depth vehicles demanded extraordinary precision and resources. Maintaining and certifying such craft required commitments few organizations were prepared to sustain. Without continuous programs, expertise dispersed, and infrastructure aged. The achievement of 1960 stood as both milestone and boundary, demonstrating possibility while quietly revealing how difficult repetition would be. In that long silence, the trench remained where it had always been, unchanged in depth, waiting beyond routine reach. Long after the first visit proved the depth could be survived, the trench remained largely undisturbed by human presence. The silence that followed was not imposed by mystery alone, but by rarity of opportunity. Returning required not only courage, but a convergence of resources that seldom aligned. As years passed, the bottom of the ocean became less a destination and more a memory preserved in technical archives. In 2012, filmmaker and explorer James Cameron descended alone to Challenger Deep in a custom-built submersible designed specifically for the journey. His dive was the result of years of engineering, development, private funding, and meticulous testing. The craft, slender and vertical in orientation, carried him downward through hours of darkness until he reached the sedimented floor. He remained there briefly, collecting samples and recording imagery before beginning the ascent. It was a singular expedition, ambitious and carefully contained, not the beginning of routine travel. Several years later, investor and former naval officer Victor Vescovo undertook a series of deep ocean expeditions, including multiple descents to the deepest known point. His program relied on a full-depth certified submersible and a dedicated support vessel capable of operating in remote waters. These missions expanded mapping efforts and gathered biological and geological data, demonstrating that repeated access was possible under the right conditions. Yet even these efforts were supported by private initiative rather than sustained international programs. When counted together, the total number of humans who have physically reached Challenger Deep remains exceedingly small. The figure stands in the single digits across more than half a century of technological advancement. By contrast, space agencies around the world conduct launches routinely. Since the dawn of the space age, thousands of rockets have left Earth's surface, carrying satellites, cargo, and crews into orbit. Human spaceflight, once extraordinary, has become a structured enterprise supported by stable budgets and coordinated infrastructure. Deep-sea exploration has not enjoyed the same continuity. Oceanographic research competes with many other priorities, often receiving a fraction of the funding allocated to space programs. The deep ocean lies out of sight, lacking the symbolic visibility of a rocket rising against the sky. Public imagination gravitates upward toward planets and stars, while the abyss remains hidden beneath layers of water that conceal both risk and reward. Without long term institutional commitment, each descent to the trench becomes an isolated endeavor. Teams assemble, vessels are prepared, and once the mission concludes, momentum dissipates. Expertise disperses across other projects, and maintenance costs weigh against uncertain returns. The result is a pattern of rare, determined visits rather than continuous presence. In this quiet arithmetic of resources and attention, the deepest point on Earth remains accessible in theory, yet seldom reached in practice. On the surface, the ocean appears open and unclaimed, yet the path to its deepest floor begins with ledgers, contracts, and careful planning spread across conference tables. Reaching the bottom is not only a technical challenge, it is an economic undertaking measured in millions for a single expedition. Funds must cover design refinements, crew salaries, fuel, port fees, satellite communications, and the quiet redundancy built into every critical system. Before a vessel ever leaves harbor, resources have already flowed outward in steady, necessary streams. A full-depth mission requires a specialized support ship capable of dynamic positioning in open ocean. Such ships are equipped with cranes, winches, laboratories, and accommodations for engineers, pilots, and scientists. They must carry spare components, diagnostic equipment, and remotely operated vehicles prepared to assist if needed. Operating costs accumulate daily, from fuel consumption to maintenance of onboard systems. The sea itself may demand extended time on station, as weather windows open and close according to conditions far beyond human control. Preparation unfolds over years rather than weeks. Engineers refine hull designs, test materials under simulated pressures, and conduct incremental sea trials at shallower depths. Certification processes involve independent review and extensive documentation. Crews train repeatedly, rehearsing launch and recovery procedures until movements become precise and unhurried. Every checklist is shaped by prior experience, every improvement reflecting lessons learned in earlier campaigns. This extended preparation represents both caution and necessity, as margins for error narrow with depth. Insurance introduces another layer of cost. Insurers assess the risk of operating at extreme depths, where recovery of equipment may be uncertain and liability complex. Premiums reflect not only the value of the submersible itself, but also the potential impact of loss on supporting vessels and personnel. Legal frameworks governing international waters add further considerations, requiring compliance with maritime regulations and environmental protections. Each of these elements contributes to the overall expense of a single descent. Because of these factors, deep trench exploration does not scale easily. Launching multiple simultaneous missions would multiply logistical complexity and financial burden. There are limited shipyards capable of constructing full-depth pressure spheres and limited crews trained to operate them. Unlike satellite launches, which can follow standardized production lines, each trench expedition resembles a bespoke project shaped by specific objectives and conditions. The combination of high cost, specialized infrastructure, and long preparation cycles constrains frequency. Access remains possible, yet it depends on concentrated investment sustained over time. In that quiet arithmetic of resources, the deepest point on Earth reveals itself not only as a physical boundary, but as an economic one as well. Departure from the surface begins in brightness, with sunlight scattering across waves and reflecting against the hull. For a short while, the water remains translucent, tinted blue by the absorption of longer wavelengths. Shadows ripple along the exterior as the vessel slips beneath the surface. Within the first 200 meters, that clarity begins to fade. Reds vanish first, then oranges and yellows, leaving a narrowing spectrum of blue that grows deeper and more subdued with each passing moment. As the descent continues, illumination weakens into twilight. The last traces of natural light thin into a dim haze, filtered through an ever thickening column of water. Beyond roughly 1,000 meters, sunlight no longer penetrates at all. The ocean becomes entirely dark, not merely dim but absolute, a space where the absence of photons is complete. External lights cast narrow beams that dissolve quickly into blackness, revealing only what lies directly ahead while the surrounding water remains unknowable. Temperature falls steadily during this journey. Near the surface, warmth lingers from solar heating and atmospheric exchange. Far below, the water stabilizes just above freezing, held in a cold equilibrium by global circulation patterns. The hull separates interior climate from exterior chill, yet sensors register the shift with quiet precision. Electronics hum softly, maintaining stable conditions while the outer shell endures an environment perpetually cold and dense. Sound behaves differently at depth. The crew hears the faint creak of metal adjusting under pressure, subtle pops as structural elements settle into their load-bearing roles. These noises are not sudden alarms, but measured reminders that forces outside are immense and continuous. Pumps circulate life support systems with steady rhythm, and instrumentation emits gentle tones as data streams across monitors. Conversation, when it occurs, is calm and deliberate, shaped by awareness of isolation. Psychological distance expands as physical depth increases. Communication with the surface relies on acoustic signals that travel slowly through water, introducing delay between transmission and response. Messages are concise, reduced to essential information. The sense of separation is not dramatic, but gradual, as if the world above recedes into abstraction. Outside the viewport, darkness presses close, broken only by the glow of the vessel's own lights. In this environment, time acquires a different texture. Hours pass marked by depth readings and system checks rather than visual landmarks. The descent becomes an inward passage as much as a downward one, a movement through layers of ocean that few will ever witness directly. By the time the seafloor approaches, the memory of sunlight feels distant, replaced by a quiet awareness of being suspended within the largest continuous habitat on Earth, far from the familiar rhythms of the surface world. When the descent finally ends, there is no towering wall waiting in the darkness, no jagged abyss dropping away into deeper shadow. The seafloor at Challenger Deep reveals itself gradually in the glow of artificial light, a broad and level expanse stretching outward beyond visibility. It resembles a quiet plain more than a chasm, its surface composed of fine sediment that has settled patiently over ages. The dramatic vertical relief, often imagined at the deepest point, gives way instead to subtle undulations shaped by slow geological processes. The sediment itself is delicate, a layer of silt so fine that the slightest disturbance lifts it into suspension. As a submersible settles, thrusters displace the uppermost grains, sending pale clouds drifting through the water. These particles descend from above over immense spans of time, formed from the remains of microscopic organisms, fragments of distant coastlines, and dust carried by wind across entire oceans. Layer upon layer accumulates in near silence, building a soft blanket across the trench floor. Within this muted landscape, life persists. Amphipods move across the sediment, their translucent bodies adapted to pressure and scarcity. They scavenge organic material that falls from higher waters, converting faint traces of energy into motion. Nearby, snailfish glide just above the seabed, their gelatinous forms lacking the rigid structures that would falter under immense compression. Their physiology reflects biochemical adjustments at the cellular level, proteins stabilized by compounds that prevent collapse under crushing conditions. In this environment, flexibility becomes strength. The scene is not crowded, yet it is not empty. Tracks etched into the silt reveal recent movement. Small burrows mark where organisms have disturbed the surface. The water above remains still, broken only by the movement of the visiting craft. Light beams fade quickly, illuminating only a narrow corridor through the dark. Beyond that corridor, the plane continues in quiet continuity. Amid this natural accumulation, evidence of distant human activity has also been found. Tiny fragments of plastic, transported by currents and sinking through the water column, have settled even here. These microplastics, scarcely visible without careful analysis, testify to the interconnectedness of ocean systems. Material discarded far from the trench can travel through gyres and deep currents, eventually descending to the lowest known point on Earth. There are no sheer cliffs enclosing Challenger. Deep at its center, no dramatic precipice framing the moment of arrival. Instead, the bottom presents itself as a vast, understated expanse shaped by gravity, time, and sedimentation. Its simplicity does not diminish its significance. The plain rests beneath miles of water, bearing the quiet record of geological motion and biological adaptation, a landscape defined less by spectacle than by endurance. Above the quiet plain of the trench rises an immense column of water, extending upward for nearly 7 miles to the surface, far beyond sight. This vertical expanse is not empty space but a continuous mass, layered by temperature, salinity, and density. Every layer rests upon the one below it, forming a stacked structure that transmits weight with unwavering consistency. The seafloor bears the cumulative load of this entire column, a pressure created not by motion alone, but by the simple presence of water drawn downward by gravity. That weight is constant, unrelieved by pauses or seasons. Unlike wind or waves at the surface, which surge and retreat, the downward force at depth does not fluctuate dramatically from moment to moment. It is the steady outcome of mass suspended above, a reminder that the trench is part of a connected system, stretching to open air. Even in apparent stillness, the ocean presses with quiet authority. Yet the water column is not static. Within it move internal waves, vast undulations that travel along boundaries where layers of different densities meet. These waves do not break visibly like those at the shore. Instead, they roll slowly through the interior, sometimes spanning great distances. As they propagate, they redistribute energy and subtly alter conditions at depth. Instruments anchored to the seabed have recorded their passage, noting shifts in temperature and current that reflect activity far above. Deep currents also thread through this vertical space, moving at measured speeds that may seem insignificant compared with surface flows. Driven by differences in density created by temperature and salinity, these currents form part of a global circulation pattern that links polar regions with equatorial waters. Over long spans of time, they transport nutrients, dissolved gases, and suspended particles from one basin to another. Material descending from higher levels may be carried laterally before settling, adding complexity to what might otherwise appear as simple vertical accumulation. Surface storms, though separated by miles of water, can influence this deep environment as well. Powerful cyclones generate pressure changes and wave energy that penetrate downward, disturbing upper layers and sometimes amplifying internal wave activity. While the direct force of wind does not reach the trench floor, the energy introduced at the surface can cascade through intermediate layers, subtly modifying current patterns below. The connection is not immediate or dramatic, but it is real. In this way, the trench is never isolated. It rests beneath a living column that responds to atmospheric shifts, seasonal cycles, and planetary rotation. The water overhead carries not only weight but motion, linking the deepest seafloor to distant coasts and polar ice. What lies at the bottom remains shaped by forces that begin in sunlight and wind, transmitted downward through layers of fluid that bind the ocean into a single, continuous body. Beneath the immense column of water, the boundary that formed the trench continues its slow negotiation. The Pacific Plate does not rest quietly beneath its neighbor. It presses and locks, storing strain along the interface where rock meets rock. Over years and decades, stress accumulates invisibly within the crust. When resistance finally yields, energy releases in earthquakes that ripple through both solid earth and surrounding sea. These events may pass unnoticed at the surface, yet at depth they alter the architecture of the trench in subtle and sometimes dramatic ways. Subduction zones are among the most seismically active regions on the planet. The descending plate bends and fractures as it sinks, creating networks of faults that can shift abruptly. Tremors propagate along the trench axis and into adjacent slopes, disturbing layers of sediment that have settled in fragile balance. Even moderate quakes can loosen accumulations resting on steep inclines, initiating undersea landslides that move with quiet force through the dark. When sediment shifts downslope, it does not simply resettle in identical patterns. Clouds of particles lift into suspension, carried briefly by currents before settling again in altered configurations. The once smooth plain may acquire new ripples or shallow depressions. In some areas, thicker deposits can blanket underlying features, while in others, freshly exposed surfaces reveal textures previously hidden. The seafloor becomes a record rewritten, its contours adjusted by each episode of tectonic motion. These changes occur at scales both minute and expansive. A single landslide might redistribute material across several kilometers, while a larger seismic event could subtly modify the depth profile of an entire segment of the trench. Bathymetric surveys capture snapshots of this landscape, tracing contours through acoustic mapping. Yet the maps represent moments in time rather than permanent truths. Between expeditions, the trench continues its quiet evolution. Because of this ongoing movement, data collected during one mission may require revision in the future. Instruments anchored to the seabed must account for potential displacement, and long-term studies incorporate uncertainty born of geological restlessness. Scientists compare successive surveys to identify shifts, analyzing patterns that reveal how the boundary behaves under sustained convergence. Each dataset contributes to a more nuanced understanding, yet none can claim finality. The trench, therefore, is not a fixed cavity carved once and preserved unchanged. It is an active margin shaped by forces operating beneath and within it. Earthquakes and sediment flows are not anomalies but integral aspects of its existence. As plates continue their gradual descent and friction builds along their contact, the seafloor responds in kind. What appears stable in the beam of a submersible's light is part of a dynamic system, adjusting over time in rhythms measured not by days, but by the slow pulse of tectonic motion. From orbit, the contours of continents are traced in sharp detail, mountains and valleys rendered with remarkable clarity. Beneath the ocean, the same precision is far more difficult to achieve. Light cannot penetrate the depths, so mapping relies on sound. Multi-beam sonar systems mounted on ships emit pulses that travel downward, reflect from the seafloor, and return to receivers. The time required for those echoes to return reveals depth, while variations in intensity suggest texture and slope. It is an elegant method, yet it carries inherent limits. Sound spreads as it moves through water, forming expanding cones rather than narrow beams. At great depths, this spreading reduces resolution. A single acoustic pulse may illuminate a wide patch of seafloor, blending small features into broader shapes. Fine ridges, shallow depressions, and subtle sediment waves can escape detection when measured from miles above. Higher frequencies offer sharper detail, but they attenuate more quickly and cannot travel the full distance to the deepest trench floor. Lower frequencies penetrate farther, yet sacrifice clarity. The choice becomes a balance between reach and precision. As a result, only portions of the Mariana Trench have been mapped at high resolution. Dedicated expeditions deploy autonomous or remotely operated vehicles closer to the seabed, carrying sonar arrays that capture finer detail. These missions produce detailed grids of specific areas, revealing textures and slopes invisible to ship-based surveys. However, such operations require time, fuel, and favorable conditions. Covering the entire length of the trench at this level of detail would demand sustained effort over many years. Between focused expeditions lie vast stretches that remain mapped only in coarse outline. Bathymetric charts may indicate general depth and major features, yet leave smaller structures unresolved. Data collected during one mission often stands alone, separated by long intervals from subsequent surveys. In those intervals, geological processes continue, subtly altering the landscape as described earlier. Without repeated mapping, it becomes difficult to determine whether observed differences reflect new changes or simply improved measurement techniques. Data gaps also arise from logistical constraints. Ship tracks rarely overlap perfectly, leaving corridors of higher resolution flanked by broader swaths of lower detail. Weather, funding, and mission priorities shape where surveys occur. The trench, extending for more than 1,000 miles, cannot be captured in a single sweep. Instead, it emerges gradually through accumulated data sets, each adding a fragment to a larger mosaic. Thus, mapping the deepest boundary is not a one-time achievement, but an ongoing process. Sound reveals much, yet not everything. Resolution fades with distance, and coverage depends on opportunity. The trench persists in partial view, charted in segments that reflect both technological capability and the limits of sustained attention. Far below the reach of sunlight, and beyond the tolerances of unprotected machinery, living cells continue their quiet work. In the deepest trench, survival does not depend on resisting pressure in the way engineered hulls must. Instead, life adapts from within. Proteins, the molecular machines that fold into precise shapes to perform specific tasks, are subtly altered in organisms that inhabit these depths. Their structures are stabilized by compounds such as trimethylamine N-oxide, which counteracts the destabilizing effects of extreme compression. Under crushing force, where ordinary proteins might lose shape and function, these variants retain their integrity. Cell membranes, too, are adjusted. In most environments, membranes maintain a delicate balance between rigidity and fluidity, allowing nutrients to pass while preserving internal order. At immense depth, Pressure tends to stiffen lipid layers, threatening to impede essential processes. Deep sea organisms compensate by incorporating specific fatty acids that preserve flexibility even under intense compression. The membrane remains permeable enough to support metabolism, yet cohesive enough to protect cellular components. This biochemical tuning allows life to operate in conditions that would render many surface organisms inert. Among the visible inhabitants of the trench floor are amphipods of unusual size, sometimes referred to as giant amphipods. Their elongated bodies move deliberately across the sediment, scavenging organic matter that drifts down from above. High pressure does not crush them because their internal structures are largely composed of incompressible fluids, and their exoskeletons are adapted to distribute force without brittle failure. Their size may reflect ecological opportunity as much as adaptation, shaped by scarce but energy rich food pulses that reach the depths. Snailfish glide through the water just above the sea floor, their bodies soft and semi transparent. Unlike shallow water fish that rely on gas filled swim bladders for buoyancy, these species lack large air spaces that would collapse under pressure. Their tissues are gelatinous, reducing density differences with surrounding water and minimizing stress on internal organs. Enzymes within their cells function efficiently despite the immense load pressing inward from all sides. Genetic studies reveal modifications in genes related to protein stability and cellular repair, subtle shifts that allow life to persist where steel must be engineered with extreme caution. Life in the trench does not conquer pressure by brute strength. It accommodates it, reshaping molecular architecture to align with physical law. Metabolic rates are often slow, energy budgets carefully balanced, yet reproduction and growth continue. In this environment, crushing force is not an occasional hazard, but a constant condition. Where human technology must erect barriers to survive, biology integrates pressure into its design. The result is a community of organisms whose existence illustrates an alternative strategy, one in which adaptation replaces resistance and endurance emerges from molecular precision. Beneath the slow movements of amphipods and the quiet glide of fish, another world unfolds at scales too small to see with unaided eyes. Within the sediment and along mineral surfaces, live communities of microbes that anchor the deepest ecosystem. These organisms do not rely on sunlight, nor do they wait passively for scraps to arrive. Many draw energy from chemical gradients embedded in the earth itself, practicing chemosynthesis in place of photosynthesis. Where compounds such as hydrogen sulfide, methane, or reduced metals seep from buried layers, bacteria harness the energy released during oxidation, building organic molecules from inorganic sources. This metabolic strategy allows life to persist independent of direct solar input. In certain pockets of the trench, fluids circulating through fractured crust deliver dissolved chemicals into the sediment. Microbial cells cluster around these microenvironments, forming thin films that coat grains and rock fragments. Their activity may be slow compared with surface blooms, yet it is continuous, unfolding under stable cold and immense pressure. Enzymes adapted to compression facilitate reactions that would stall in organisms unaccustomed to such conditions. Alongside chemosynthetic pathways, the trench receives a steady, though sparse rain of organic matter from above. Microscopic plankton that lived and died in sunlit waters drift downward over weeks and months, gradually decomposing as they descend. By the time these particles reach the abyss, much of their energy has been consumed by intermediate communities. What remains settles into the sediment as marine snow, a faint residue of distant productivity. Microbes within the seabed metabolize this material, breaking complex compounds into simpler forms and recycling carbon into dissolved pools. Carbon cycling at these depths operates on extended timescales. Organic matter may persist for years within fine silt before complete decomposition. Some carbon is buried, incorporated into layers that may eventually be drawn into the subducting plate, linking biological processes with tectonic motion. Other fractions return to the water column as dissolved inorganic carbon, contributing to the broader chemistry of the ocean. In this way, the trench participates in planetary cycles despite its remoteness. Sediment ecosystems are structured vertically as well as horizontally. Oxygen penetrates only a short distance into the seabed before being consumed by respiration. Below that thin oxic layer, microbes switch to alternative electron acceptors, such as nitrate or sulfate, enabling metabolism in the absence of free oxygen. Each depth within the sediment hosts distinct communities adapted to available resources and chemical conditions. The result is a layered biosphere hidden beneath the surface plane, one that processes energy with patience and efficiency. Though invisible during a brief visit, this microbial network forms the foundation of life at the deepest boundary. Its persistence illustrates that even under crushing pressure and near freezing temperatures, biochemical pathways continue, quietly sustaining an ecosystem built from chemistry and time. At the surface, communication moves with near invisibility. Signals pass through air and space at the speed of light, linking continents in fractions of a second. Beneath the ocean, that effortless exchange dissolves. Water absorbs radio waves rapidly, especially at the frequencies used for conventional transmission. Within a short distance, electromagnetic signals weaken into silence. The deeper one travels, the more complete that silence becomes. A submersible descending toward the trench cannot rely on the invisible networks that shape modern life above. Instead, communication shifts to sound. Acoustic systems convert messages into pulses that travel through water as pressure waves. These signals move far more slowly than light, progressing at roughly 1,500 meters per second, depending on temperature and salinity. Over distances measured in miles, this speed introduces noticeable delay. A message sent from the surface may take several seconds to reach a vessel at depth, and a reply requires the same measured patience. Conversation becomes an exchange marked by pauses rather than immediacy. Bandwidth at such depths is limited. Acoustic channels cannot carry large volumes of data quickly. High-resolution video streams that flow easily through fiber optic cables are impractical through water alone. Instead, compressed packets of information are transmitted in brief bursts. Telemetry reports depth, orientation, internal pressure, and life support status in concise formats. Images may be stored on board for later retrieval rather than sent continuously upward. The trench, therefore, is experienced in fragments by those waiting above. Environmental conditions further complicate transmission. Layers within the water column bend and scatter sound waves, creating variations in signal strength. Background noise from distant ships, shifting sediments, or even biological activity can interfere with clarity. Engineers compensate by selecting specific frequencies and adjusting power levels, yet interference cannot be eliminated entirely. Communication remains functional, but never effortless. The delay inherent in acoustic exchange shapes decision-making. Pilots operating at full depth must rely primarily on onboard judgment rather than constant direction from the surface. Instructions are brief and deliberate, crafted to account for the time between sending and receiving. Autonomy becomes essential. Systems are designed to function independently should contact weaken or temporarily fail. Redundant protocols ensure that life support and ascent mechanisms do not depend solely on external confirmation. In this environment, the connection between surface and depth feels stretched across distance, both physical and temporal. Messages travel, but they do so with measured pace. The trench is not cut off from the world above, yet it is never fully synchronized with it. Communication persists as a thin acoustic thread, linking two vastly different realms through sound carried patiently across miles of water. Imagine, for a moment, a structure resting on the trench floor not for hours, but for years. Steel and composite would no longer endure pressure as a temporary burden during descent and ascent. They would live beneath it continuously. The difference between brief exposure and permanent residence is profound. Materials that tolerate compression for a limited duration begin to experience cumulative effects when subjected without interruption. Microscopic fatigue, subtle deformation, and long-term creep would gradually alter structural integrity, even in alloys engineered for strength. At full depth, external pressure does not fluctuate in comforting cycles. It remains constant, pressing inward with unwavering force. A permanent habitat would require thick walls shaped to distribute stress evenly, yet those walls would still age under continuous load. Inspection and repair, routine in shallow environments, would be extraordinarily complex here. Every seal, viewport, and joint would demand monitoring, yet direct human access for maintenance would be constrained by the very conditions the structure sought to withstand. Energy presents another challenge. Powering life support systems, lighting, scientific instruments, and communication arrays requires a reliable supply. At the surface, vessels draw fuel or connect to established grids. On the trench floor, no such infrastructure exists. Batteries provide limited duration. Nuclear options introduce regulatory and safety considerations. Renewable sources such as solar or wind are inaccessible in perpetual darkness and stillness. Tethered cables extending miles upward would themselves endure immense strain, vulnerable to currents, seismic movement, and mechanical fatigue. Logistics compound the difficulty. Supplying a permanent base would require repeated descents carrying food, spare parts, medical equipment, and research tools. Each delivery would depend on specialized vehicles capable of reaching full depth, subject to the economic and technical constraints already described. Waste removal and system upgrades would follow similar pathways, tying the base to a fragile chain of support. Any interruption in that chain, whether due to funding shifts, mechanical failure, or weather at the surface, could compromise operations below. Even autonomous systems would not escape these limitations. Robotic habitats still demand power, data links, and periodic servicing. The trench is not a stable platform but an active geological boundary where sediment shifts and seismic tremors can alter the landscape. Anchoring structures securely would require accounting for movement that unfolds over years and decades. For these reasons, the vision of a permanent human outpost at the deepest point remains impractical with current technology. The ocean floor at such depth resists occupation not through hostility alone, but through the steady accumulation of demands. Structural endurance, continuous maintenance, dependable energy, and intricate supply chains converge into a complexity that exceeds present capacity. The trench remains a place visited with care, rather than settled in permanence. Beyond the atmosphere, space appears hostile in ways that are immediate and stark. It is a vacuum, absent of air and unshielded from radiation, yet its hostility differs fundamentally from that of the deep ocean. In orbit, a spacecraft contains its own internal pressure, gently pushing outward against the void. The structural challenge is to prevent expansion and leakage, to maintain a controlled environment within thin walls. In the trench, the direction of force reverses. Water presses inward from every angle, demanding resistance against compression rather than containment against escape. Materials behave differently under these opposing conditions, and in many respects, holding back emptiness proves simpler than resisting relentless weight. Communication in orbit benefits from electromagnetic transmission. Radio waves travel freely through vacuum, linking spacecraft to ground stations with minimal delay. High bandwidth connections allow continuous streams of data, voice, and imagery. Astronauts aboard orbital platforms can speak with mission control in near real time, receiving guidance and transmitting observations without significant pause. In the trench, as described earlier, acoustic signals move slowly and carry limited information. The contrast in immediacy shapes operational flexibility. Rescue possibilities also differ. In low Earth orbit, spacecraft trajectories are calculated precisely, and launch windows can be planned to coincide with potential contingencies. If a vehicle experiences difficulty, other missions can sometimes be organized within feasible timeframes. The distance, while immense, is predictable and unobstructed by fluid resistance. In the deep sea, rescue operations face the barrier of miles of water, pressure that increases with every meter, and vehicles that descend and ascend over hours. Immediate intervention is constrained not only by distance, but by the scarcity of full-depth capable craft. Public perception and funding patterns further widen the divide. Space exploration carries symbolic resonance, representing technological progress and national achievement. Rockets rising against the sky provide visible spectacle, and images of planets and galaxies capture imagination readily. As a result, space agencies often receive sustained budgets and long-term planning frameworks. The deep ocean, concealed beneath opaque water, lacks that same visual drama. Its discoveries unfold in darkness, shared through delayed footage and technical reports rather than live broadcasts. None of this diminishes the challenges of spaceflight. Radiation exposure, microgravity effects, and the hazards of launch remain significant. Yet, in certain logistical and communicative aspects, orbit offers advantages absent at full ocean depth. The vacuum does not press inward with crushing force, and signals traverse it with ease. When measured against the trench, the boundary of space can appear, in specific ways, more accessible. The contrast reveals that difficulty depends not only on distance, but on the medium through which exploration must pass. Across shipyards and research institutions scattered around the world, only a small collection of vessels possess the capability to reach the deepest trench. These are not mass-produced machines rolling from assembly lines. Each full-depth submersible represents years of design, refinement, custom fabrication, and specialized testing. Their number can be counted on one hand, and at any given time, not all remain operational. Availability depends on maintenance cycles, funding allocations, and the careful scheduling of expeditions that may be years in planning. Unlike surface ships that can be dry docked with relative ease, full-depth submersibles require inspection protocols shaped by extreme exposure. After each descent, engineers examine pressure spheres for microfractures, analyze data logs for anomalous stress patterns, and evaluate seals that endured hours under immense load. Non-destructive testing methods, Search for hidden fatigue within metal and composite layers. Even when no visible damage appears, caution governs decisions about future dives. The absence of failure does not guarantee immunity from cumulative strain. Maintenance itself demands expertise that is both rare and highly technical. Specialists familiar with deep ocean engineering must interpret subtle signs of wear, often relying on experience drawn from a limited number of comparable vehicles. Replacement components cannot be sourced casually. Pressure resistant viewports, specialized alloys, and precision machined joints are produced in small quantities by companies accustomed to working within narrow tolerances. Lead times for fabrication extend months or even years, particularly when materials must meet stringent certification standards. Replacement timelines for entire submersibles are longer still. Designing and constructing a new full-depth vehicle involves extensive modeling, prototype testing, and review by independent authorities. Funding must be secured not only for construction but also for sea trials and operational support. Shipyard space capable of handling such projects is limited, and builders with the necessary experience are few. Knowledge is concentrated within a small community of engineers and fabricators who understand how to shape materials for survival at extreme depth. Because of this concentration, the global fleet ages in parallel. Vehicles built within similar eras progress through comparable maintenance challenges over time. Upgrades extend operational life, yet no machine escapes the gradual accumulation of wear. If one vessel retires, the gap it leaves is not easily filled. The continuity of deep exploration depends on careful stewardship of this small fleet and on the sustained cultivation of expertise required to replace it. In this context, access to the trench is tethered to machines that are both extraordinary and finite. Their longevity relies on meticulous care and ongoing investment. Without deliberate renewal, the number of capable vehicles could diminish quietly, narrowing the pathway to the deepest boundary once more. Progress at extreme depth does not move forward in a straight line. It advances cautiously, measured not only by engineering success, but by collective confidence. In environments where margins are narrow and consequences immediate, tolerance for risk remains low. A single serious accident can shift the trajectory of exploration for years, not through technical impossibility alone, but through changes in perception and policy that ripple outward. When an incident occurs in deep ocean operations, investigations follow with careful scrutiny. Engineers analyze structural data, material performance, procedural decisions, and environmental conditions. Regulatory bodies review findings and often introduce revised standards intended to prevent recurrence. Certification requirements may tighten, inspection intervals shorten, and design thresholds increase. These changes enhance safety, yet they also lengthen development timelines and raise costs. Projects already operating near financial limits can stall under additional layers of oversight. Regulation is not imposed arbitrarily. It reflects a societal expectation that high-risk endeavors demonstrate clear justification and robust safeguards. In the case of deep submersibles, where failure unfolds rapidly and rescue is constrained by physics, authorities tend toward conservatism. Approval processes expand to incorporate new testing protocols, simulation requirements, and documentation standards. Each revision strengthens structural reliability, yet collectively they slow momentum. Public perception plays an equally significant role. Dramatic headlines capture attention more readily than incremental scientific achievement. When tragedy strikes in any high-profile expedition, images and narratives circulate widely, shaping emotional response. Even when investigations reveal complex technical causes rather than simple negligence, the broader impression can linger. Funding agencies, mindful of public sentiment and political accountability, may redirect resources toward projects perceived as less hazardous or more immediately beneficial. Deep sea exploration already competes with numerous priorities, from climate research to infrastructure and health initiatives. In such an environment, tolerance for visible risk diminishes quickly. Sponsors and institutions weigh potential gains against reputational and financial exposure. If confidence erodes, programs can pause indefinitely while new safety frameworks are debated and implemented. Expertise disperses, ships return to other duties, and momentum fades. This pattern has appeared in other domains of exploration as well. High consequence environments demand resilience not only in materials but in institutional commitment. Sustained access depends on a delicate balance between ambition and caution. When that balance tilts sharply in response to a single event, the pathway downward narrows. The trench itself remains unchanged, yet human willingness to approach it can contract, shaped by collective judgment as much as by engineering capability. Each descent to the trench begins almost as if it were the first. Teams assemble, vessels are outfitted, checklists are reviewed, and once the mission concludes, much of that temporary structure dissolves again. There is no permanent dock suspended above the deepest point, no anchored platform marking a fixed route downward. Every expedition stands largely on its own, shaped by its particular objectives, budget, and timing. Continuity exists in data archives and shared expertise, yet physically, the pathway must be rebuilt each time. Without infrastructure embedded at depth, operations cannot accumulate incremental convenience. There are no refueling stations along the way, no stored supplies waiting at intermediate levels. Launch and recovery depend on surface. Ships positioned carefully over coordinates, calculated anew for each mission. Dynamic positioning systems maintain alignment against currents and wind, yet once the vessel departs, the ocean erases all visible traces of presence. The trench does not retain a footprint of prior visits. Scientific opportunity windows are often narrow. Weather patterns influence when ships can operate safely in the Western Pacific. Storm seasons, sea state, and logistical constraints at ports limit available time at sea. Even when a vessel reaches the trench, dive durations are constrained by battery capacity, life support reserves, and scheduling requirements. Hours at depth represent years of preparation condensed into brief observation and sampling periods. Once ascent begins, the opportunity closes until resources align again. Research goals must therefore be prioritized carefully. Instruments are calibrated to collect as much information as possible within limited intervals. Sampling strategies are planned in advance because improvisation at depth is restricted by communication delays and energy constraints. The absence of permanent installations means that long-term monitoring relies on devices deployed temporarily and later retrieved, rather than on continuous human oversight. Gaps between missions can span years, leaving evolving processes undocumented in real time. Funding cycles further fragment continuity. Grants are awarded for defined periods, after which renewal depends on demonstrated results and shifting institutional priorities. A successful expedition may secure subsequent support, yet delays between approvals can interrupt momentum. During those pauses, crews disperse to other projects, ships undertake different assignments, and specialized knowledge risks dilution. Reassembling that network requires renewed coordination and commitment. Because each dive is effectively standalone, repeat access becomes rare, not through impossibility, but through accumulation of practical limits. The trench remains in place, unchanged in depth, yet human presence touches it intermittently. Between visits, miles of water and months of planning separate one descent from the next. In this pattern, access exists as a sequence of moments rather than a continuous thread, dependent on alignment of conditions that cannot be sustained indefinitely without enduring infrastructure. National budgets are finite expressions of collective choice. Each fiscal year, governments and institutions weigh demands that span health, infrastructure, education, defense, climate resilience, and technological development. Within this broad landscape, oceanographic research competes quietly for allocation. The deep trench, remote and largely invisible, does not present itself as an urgent crisis, nor as a widely understood opportunity. Its needs are measured against challenges that affect daily life more directly, and in that comparison, it often recedes. Research funding follows priorities shaped by public perception and political momentum. Programs addressing visible disasters or immediate economic returns tend to attract sustained support. Space exploration, renewable energy, and medical innovation generate narratives that resonate across borders. The deep ocean, by contrast, unfolds in darkness, its discoveries emerging gradually through technical reports rather than live spectacle. Even when findings hold profound scientific value, they rarely command headlines for long. Budget limitations impose practical boundaries. Oceanographic vessels are expensive to operate. Specialized crews require ongoing training, and full-depth, capable submersibles demand maintenance budgets that extend beyond single expeditions. When funding cycles tighten, institutions may prioritize projects with broader participation or clearer short-term impact. Deep trench missions, requiring concentrated resources for limited duration, can be deferred without immediate consequence to national infrastructure. International collaboration offers potential relief, yet coordination across agencies introduces complexity. Shared funding arrangements must navigate differing regulations, strategic interests, and administrative timelines. In the absence of unified long-term frameworks, initiatives depend on temporary agreements. A change in leadership or economic downturn can redirect support swiftly. The trench itself remains unchanged, but human commitment to reaching it fluctuates with shifting priorities. Politically, the deep ocean occupies an ambiguous space. It is not contested territory in the conventional sense, nor is it a frontier promising rapid commercial return. Its value lies in knowledge, in understanding planetary processes, biodiversity, and long-term environmental change. Such benefits unfold over decades, aligning with scientific curiosity more than immediate policy objectives. When policymakers assess competing demands, investments whose rewards are diffuse and delayed may struggle to maintain prominence. Economic reality, therefore, shapes access as decisively as physics. The capacity to descend depends on sustained allocation of resources that must be justified repeatedly. In prosperous periods, exploration may flourish. During constraint, it may pause. The trench does not move in response to budgets, yet human pathways toward it narrow or widen according to decisions made far from its depths. In this interplay between curiosity and cost, the deepest boundary becomes subject not only to geological forces, but to economic ones as well. There is a quiet difference between arrival and belonging. When a vessel settles briefly upon the deepest seafloor, instruments record depth, cameras capture images, and headlines may announce that humanity has reached the bottom. The language suggests completion, as though a boundary once distant has been crossed and secured. Yet the trench does not become familiar through a single visit. It remains as it was before, shaped by pressure and motion, unchanged by the fleeting presence of lights and metal. Touching a place is not the same as sustaining presence within it. A footprint pressed into sediment at depth dissolves in drifting silt. Once ascent begins, the ocean resumes its uninterrupted rhythms. No path remains carved through the water column, no marker fixed to guide return. The achievement lies in demonstration of capability rather than in transformation of environment. To say that the bottom has been reached is accurate, yet it risks implying a permanence that does not exist. Media framing often favors clarity and finality. Phrases such as first descent or deepest dive carry symbolic weight. They resonate because they echo familiar narratives of summits attained and frontiers crossed. In scientific reality, however, exploration unfolds as an ongoing process. Data collected during a single mission contribute to broader understanding, but they do not exhaust the questions that remain. The trench is vast in length and complex in structure. Sampling one site does not equate to comprehensive knowledge. Exploration differs fundamentally from occupation. Occupation implies infrastructure, repeated access, and integration into routine activity. It suggests that a place has entered a network of sustained human use. The trench, by contrast, resists such integration. Each expedition stands apart, dependent on preparation that must be renewed. There are no permanent research stations at full depth, no continuous monitoring conducted by crews living beneath the sea. Presence is intermittent, measured in hours rather than years. The illusion of conquest arises not from arrogance but from narrative habit. Humans mark milestones and celebrate extremes, translating technical feats into symbolic achievements. In doing so, it becomes easy to equate a single descent with mastery. Yet mastery implies control, and control remains elusive at the deepest boundary. Access depends on alignment of technology, funding, and institutional will. When those elements disperse, the trench recedes from reach once more. The ocean does not recognize declarations. It responds only to physical interaction. A submersible arrives, observes, and departs, leaving the seafloor to its own processes. In this quiet cycle, the difference between having visited and having secured, enduring access becomes clear. The deepest place on Earth may have been touched, but it has not been incorporated into daily human presence. The distinction, though subtle, reshapes how achievement is understood. Every descendant subjects engineered materials to a conversation with pressure that is both precise and unforgiving. Metals and composites are not static substances. They are arrangements of atoms and fibers that respond incrementally to load. When a pressure sphere travels to full depth and returns, its structure experiences a complete cycle of compression and release. On a single dive, the deformation may remain well within design limits. Over many cycles, however, subtle changes accumulate. Fatigue emerges not as dramatic failure, but as microscopic rearrangement along grain boundaries and bonding interfaces. In metals, repeated stress can initiate tiny cracks that propagate slowly with each subsequent exposure. Even when inspections reveal no visible damage, internal stresses may linger in regions difficult to observe directly. Advanced alloys are engineered to resist such progression, yet they cannot eliminate it entirely. Predicting the exact lifespan of a component exposed to extreme depth involves modeling that relies on assumptions about load distribution, temperature stability, and material uniformity. Real world conditions introduce variability that no simulation can fully capture. Composite materials introduce further complexity. Their appeal lies in high strength to weight ratios and the ability to tailor properties through layered construction. Fibers embedded in resin matrices distribute stress in controlled ways, offering potential advantages over traditional metals. Yet long term behavior of composites under repeated full depth compression remains an area of ongoing study. Interfaces between fibers and matrix can degrade subtly over time, particularly when exposed to cyclic loading. Detecting internal delamination or microvoid formation requires sophisticated imaging techniques, and even then, interpretation demands caution. Inspection after deep dives presents practical limits. Non destructive evaluation methods, such as ultrasonic testing, radiography, and acoustic emission analysis, provide insight into internal structure. However, resolution diminishes with thickness, and certain flaws may lie below detection thresholds. Dismantling a pressure sphere for complete examination would compromise its integrity, so engineers rely on indirect measures and statistical confidence. Maintenance schedules are designed conservatively, yet uncertainty cannot be removed entirely. As vehicles age, replacement decisions become judgments, balancing cost, risk, and confidence in residual strength. Retiring a submersible prematurely limits access. Extending service life increases exposure to cumulative fatigue. This tension underscores a broader reality. Materials operate within boundaries defined by physics and chemistry. While innovation expands those boundaries, it does not render them infinite. There may come a point where incremental improvements confront diminishing returns. Stronger alloys, refined composites, and enhanced inspection methods can extend capability, yet the fundamental challenge of resisting immense, repeated compression persists. The trench exerts the same force on every descent. In response, engineering advances steadily, but always within the constraints of matter itself. Long after the lights of a submersible fade and the hum of its systems recedes toward the surface, the trench remains, receiving what the wider ocean delivers. It is easy to imagine such depth as isolated, sealed away from human influence by miles of water, yet currents link the surface and abyss in quiet continuity. What enters the sea rarely stays where it began. Over time, fragments of human industry descend through the water column, joining the slow rain of natural debris. Microplastics have been identified even within sediments at the deepest point. These particles, often smaller than grains of sand, originate from degraded packaging, synthetic fibers, and industrial waste. Carried by gyres and sinking currents, they travel vast distances before settling into silt. Their presence in the trench underscores the interconnectedness of ocean systems. Even the most remote boundary reflects activities conducted far above, in cities and coastlines unaware of their distant imprint. Beyond passive contamination lies the prospect of active extraction. Advances in marine technology have sparked interest in deep sea mining, particularly in regions rich with polymetallic nodules and mineral deposits. While the trench itself is not currently a primary target for large scale operations, its proximity to tectonically active zones and mineral resources invites speculation. Extracting materials from extreme depths would require heavy machinery capable of disturbing sediment layers that have accumulated over millennia. The ecological consequences of such disturbance remain uncertain. Ecosystems at full depth operate on slow cycles. Organic input is limited, metabolic rates are often reduced, and population growth proceeds gradually. When physical disruption occurs, recovery may extend across decades or longer. Sediment plumes generated by mechanical activity could smother benthic communities, altering habitats in ways difficult to reverse. Unlike shallow environments where sunlight accelerates biological turnover, the trench offers no rapid renewal. Scientific understanding of these ecosystems is still developing. Many species have been observed only briefly, their life histories inferred from limited samples. Microbial networks, described earlier, form intricate relationships with geochemical gradients and sediment structure. Disturbance at scale could shift these relationships in unpredictable directions. Because repeat access to the trench is already rare, long term monitoring of environmental change presents additional challenges. The environmental question, therefore, extends beyond curiosity. It invites reflection on responsibility. The trench is not merely a physical boundary to be reached, but a living system shaped by delicate balances. Plastic fragments that arrive without intention and proposals for extraction that may follow deliberate planning both illustrate how human presence reaches downward. The depth does not grant immunity from influence. Even at the farthest limit, actions taken at the surface reverberate through layers of water, settling quietly into the most remote corners of the planet. Inside a pressure sphere at full depth, space is measured not in rooms but in arm's reach. The interior is compact by necessity, every surface curved to distribute external force. Instruments line the walls, cables trace deliberate paths, and seating is arranged with efficiency rather than comfort in mind. Movement is limited. Pilots and observers remain seated for hours, aware that the boundary between themselves and the surrounding ocean is measured in inches of engineered material. Claustrophobia does not always announce itself dramatically. It can begin as a subtle awareness of confinement, a recognition that there is no corridor to walk down, no window that opens to fresh air. Even those trained extensively for such conditions must reconcile with the knowledge that ascent requires time. Once descent is complete, departure cannot be immediate. Ballast systems must function properly. Batteries must retain sufficient charge, and procedures must be followed methodically. Patience becomes part of survival. Darkness deepens this experience. Beyond the reach of exterior lights, there is no visual reference, no horizon or distant glow. The absence of natural cues can alter perception of time. Minutes stretch within a silent environment where external motion is minimal. Internal sounds, the quiet hum of systems, and the faint adjustments of structure gain prominence. The mind attends closely to these details, interpreting them through layers of training and discipline. Isolation awareness is equally tangible. Communication with the surface, as described earlier, carries delay and limitation. Responses arrive after pauses that emphasize separation. The crew knows that they are suspended beneath miles of water beyond immediate assistance. This knowledge does not need to be dramatic to be profound. It sits quietly in the background of every action, shaping decisions and reinforcing reliance on preparation. Human limits under pressure extend beyond physical tolerance. Physiological systems inside the sphere remain near surface conditions, yet psychological resilience must adapt to context. Training addresses emergency procedures, equipment failure scenarios, and prolonged confinement. Simulations replicate aspects of the environment, yet the reality of depth cannot be fully rehearsed on land. The awareness of consequence is constant, even when operations proceed smoothly. Despite these challenges, individuals continue to undertake such descents. Curiosity and commitment coexist with caution. The psychological barrier is not insurmountable, but it is real. It reflects the interplay between human cognition and the extreme environment. In the trench, engineering provides protection, yet the mind must also navigate the constraints of space, time, and separation. The boundary at depth is therefore not solely geological or mechanical. It is internal as well, defined by how humans inhabit confined spaces beneath immense and unseen weight. For the deepest point on Earth to become a place visited regularly rather than rarely, change would have to occur not only in engineering, but in structure and commitment. Routine access depends on reliability first. Vehicles would need to demonstrate consistent performance across repeated descents, with maintenance cycles predictable and manageable. Designs would have to balance strength with serviceability, allowing inspection and refurbishment without prohibitive cost or extended downtime. Confidence would grow not from a single successful mission, but from a sequence of uneventful returns. Affordability would follow reliability. If full depth, capable submersibles could be produced and operated at lower cost, the barrier to entry would shift. This does not imply compromise in safety, but refinement in manufacturing processes, supply chains, and standardization. Presently, each vessel represents a highly customized project. To make returns routine, aspects of construction would need to evolve toward modular components and reproducible systems. Broader participation from industry could reduce lead times and diversify expertise. Multiple full depth submersibles operating concurrently would further transform access. Redundancy would allow one vehicle to undergo maintenance while another conducts research. Comparative data from different expeditions could be gathered within shorter intervals, reducing gaps in observation. A fleet, rather than a singular craft, would mitigate the risk of exploration, pausing entirely if one machine retired. Such an expansion would require coordinated investment across institutions and nations. Stable, long-term funding would anchor these developments. Research programs spanning decades, rather than individual grant cycles, would provide continuity. Scientists could plan longitudinal studies of biological communities, sediment processes, and tectonic change with expectation of regular sampling. Training pipelines for pilots, engineers, and technicians would become sustained rather than intermittent, preserving specialized knowledge within dedicated teams. Infrastructure at ports and shipyards would align with predictable operational schedules. Continuous research programs would also encourage innovation in communication and autonomous systems. Data collected at depth could feed into integrated models of ocean dynamics and planetary cycles, linking trench observations with broader environmental understanding. As familiarity increased, operational procedures would refine, further reducing cost and uncertainty. Achieving this level of routine presence would require alignment of technology, economics, and policy. It would reflect a decision to treat the deepest ocean not as an occasional destination, but as a domain deserving ongoing attention. Such a shift would not erase the physical challenges described earlier, yet it would normalize them within established systems. The trench would remain immense and pressurized, but human access would become less episodic, shaped by steady investment rather than isolated ambition. Access to the deepest boundary does not expand automatically with time. It can contract as easily as it grows. Technologies that once represented the forefront of capability gradually age even when maintained with care. Electronics become obsolete, replacement parts grow scarce, and engineers familiar with legacy systems retire or move to other fields. What was once cutting edge slowly becomes difficult to support, not because it fails outright, but because the ecosystem around it thins. Full depth submersibles and their supporting vessels depend on networks of suppliers, technicians, and institutions that must remain active to sustain operations. When expeditions are infrequent, those networks weaken. Specialized manufacturers may shift focus to more profitable markets. Skilled welders and machinists, trained for extreme tolerances, may apply their expertise elsewhere. Knowledge, if not exercised regularly, disperses. Each year, without dissent, narrows the circle of those directly experienced in navigating the trench. Funding cycles, as noted earlier, rarely align with geological timescales. Research budgets are reassessed annually or over short strategic horizons. Economic downturns, political transitions, or global crises can redirect resources quickly. Programs that rely on consistent investment may find themselves deferred in favor of more immediate concerns. Once paused, reassembling the financial and institutional momentum required for deep exploration can take years. As expeditions become rare, they also become more vulnerable to disruption. A single canceled mission due to weather, mechanical complication, or budget revision may represent the only planned descent within a given period. Data gaps widen and opportunities to refine technique diminish. The trench does not signal its availability. It waits, indifferent to human scheduling. It is human systems that must remain aligned to reach it. The fragility of deep access lies in this interdependence. Technology must remain functional, funding must persist, expertise must be cultivated, and public support must not erode. Remove one element, and the chain weakens. Unlike destinations supported by permanent infrastructure, the trench relies on episodic convergence. Its accessibility is therefore contingent rather than guaranteed. There is no dramatic closure when access fades. No visible barrier rises from the sea. Instead, years pass without descent, equipment ages in storage, and plans remain proposals. The boundary remains physically unchanged, yet practically distant. The window through which routine access might be secured could narrow quietly, shaped by forces external to the ocean itself. In this way, the deepest place on Earth stands as both a geographic extreme and an institutional challenge, dependent on continuity that must be chosen and sustained. To reach a place can mean many things. It can describe a moment of contact, a brief arrival marked by instruments and observation. Yet, in quieter terms, reach implies continuity. It suggests not only the ability to descend once, but to return repeatedly without rebuilding the pathway from the beginning each time. In this deeper sense, reach becomes less about a singular achievement and more about sustained relationships. Sustained access would allow the trench to shift from episodic destination to ongoing field site. Researchers could plan multi-year studies with confidence that samples collected today might be compared with those gathered next season. Biological changes, sediment redistribution, and subtle tectonic adjustments could be traced through time rather than inferred from isolated snapshots. Patterns would emerge with greater clarity when observation extends beyond rare intervals. Routine presence does not require constant human occupation at full depth, but it does require predictability. Vehicles would travel downward on scheduled cycles. Data streams would be integrated into broader oceanographic networks. Maintenance and replacement of equipment would follow established protocols rather than ad hoc arrangements. In such a framework, the trench would remain remote, yet it would be woven more tightly into scientific practice. Detailed mapping would deepen this integration. High-resolution surveys repeated over years could reveal how slopes evolve after seismic events, how sediment layers shift, and how habitats respond to disturbance. Three-dimensional models refined through successive passes would replace coarse outlines. Knowledge would accumulate incrementally, building confidence not through dramatic milestones, but through careful repetition. Scientific continuity depends on infrastructure that supports both descent and analysis. Laboratories on shore, data repositories, trained crews, and coordinated funding streams form the unseen foundation of reach. Infrastructure does not eliminate risk or challenge, but it stabilizes intention. When systems persist beyond individual expeditions, exploration becomes less vulnerable to interruption. Yet, even with these elements in place, the trench would not become ordinary. Pressure would remain immense, darkness complete, geology active. Reach, in its fullest meaning, would coexist with respect for limits. It would acknowledge that access is maintained rather than conquered, renewed rather than assumed. In this light, the question of whether humanity has reached the deepest place becomes layered. A single descent demonstrates possibility. Sustained access would signify commitment. Routine presence would reflect alignment of technology, resources, and curiosity over time. The distinction between touching and truly reaching lies in continuity, a thread that must be held deliberately if it is not to fray. There are moments in history that feel permanent when they happen, as though a threshold once crossed will remain open indefinitely. The descent to the deepest point on Earth carried that quiet sense of arrival. Human voices traveled downward, instruments settled into silt, lights traced the outline of a place no one had seen directly before. For a brief span of time, the bottom was not an abstraction but a visited location, recorded and confirmed. Yet access is not the same as ownership. The path downward depends on machines that do not renew themselves. Hulls endure compression that leaves no visible scar, yet alters crystalline structures deep within metal. Seals harden subtly. Wiring insulation grows brittle. Even when carefully maintained, materials accumulate history. Fatigue does not announce itself loudly. It advances in microscopic increments, cycle after cycle, dive after dive. Replacement is neither swift nor simple. Designing a vessel capable of full ocean depth requires rare expertise, specialized fabrication, and years of iterative testing. Each pressure sphere represents a balance between theoretical strength and practical limits of machining and welding. Composite materials promise reduced weight, yet their long-term behavior under repeated extreme compression remains only partially understood. Inspection after descent reveals much, but never everything. Absolute certainty remains out of reach. Funding, too, follows its own tides. National priorities adjust. Economic pressures redirect attention. Research budgets expand in some seasons and contract in others. Programs built over decades can narrow quietly when resources thin. A single high-profile incident can accelerate caution, reshaping regulatory landscapes and insurance thresholds. Momentum that once felt steady can soften without ceremony. Above, the planet continues its slow rearrangement. Tectonic plates converge millimeter by millimeter. Earthquakes ripple through subduction zones, redistributing sediment in darkness. Maps drafted with care gradually lose precision as slopes shift and plains settle. The trench is not a static monument awaiting inspection. It is an active boundary shaped by forces indifferent to observation. Through all of this, the deepest place does not adjust itself for convenience. Pressure remains immense, cold persists, distance from the surface does not diminish. The environment does not become more forgiving with time. It simply endures, unchanged by whether humans choose to descend again. We have touched that floor. Evidence of presence exists in samples, recordings, and memory. Yet touch is a moment, and continuity demands sustained commitment. If machines age beyond renewal, if materials reach limits that cannot be economically replaced, if priorities shift elsewhere, the pathway narrows. Access can fade not with dramatic closure, but with gradual absence. In that quiet possibility lies a boundary unlike most others. It is not guarded by walls, but by physics and patience. It does not forbid return, it merely waits. Whether descent becomes routine or remains rare depends not on the trench itself, but on the fragile systems above it. And so the deepest place on Earth may stand as something humanity once reached, luminous in record, distant in practice, resting beneath miles of water that continue their slow, unbroken weight.